Well, good morning, good evening, and good night to everybody. Today we're going to start working on Chapter 3, Describing Relationships, and we're going to be working on Section 3.2, Least Squares Regression. As we go through, we can see that in least squared regression, we have a lot of things that we're going to talk about. So we'll start this off with the ambition of having one big video, but I'm sure we'll probably have a couple. So after this entire section, you want to be able to interpret the slope and y-intercept of the least squared regression line, use the least squared regression line to predict y for a given x, calculate, interpret residuals and their standard deviation, explain the concepts of least squares, determine the equation of the least squared regression line using a variety of methods, construct and interpret residual plots to assess whether a linear model is appropriate, and assess how well the least squared regression line models a relationship between two variables. We'll also describe how slope, the y-intercept, the standard deviation of the residuals, and r squared are influenced by outliers. So the first thing we want to talk about is what is the regression line? And depending on when you came through Algebra 2 or what they were focusing on, you might have also heard this as a line of best fit, okay? So when you have a straight line or a linear relationship between two quantitative variables, it's very easy to understand what we have here. A regression line really summarizes that relationship between them, but only in settings where the variables helps explains or predicts each other. So if we take a look here, we see this regression line. It's cutting through here. It says a regression line is a line that describes how the response variable y changes as the explanatory variable x changes. We often use a regression line to predict the value of y. So again, this is really the big idea, what we want here. We're looking for a prediction here. We have some points, we build a line through that model, and we use that to predict. So you can see a very natural relationship is we have a vehicle here. This is the miles driven versus the price for Ford F-150 trucks. And you can see as X increases, as the miles go up, the price decreases. This goes down. This has a negative slope here, or this is a negative association here, negative relationship. So what we do is we try to build that line. We use that line. It's kind of like, it's not perfect, but it's a model for the data. Much like when we're doing density curves, just like the normal curve is a density curve that sometimes can help model our data. So the equation regression line gives a compact mathematical description of what this model tells us about the relationship between the response variable y and the explanatory variable x, okay? So suppose that we have y as a response variable. That's plotted on the vertical axis, vertical like up and down, and x is the explanatory variable on the horizontal axis, like the horizon, okay? So the regression line, y to x, looks like this. Y hat equals a plus bx. And so how we read that with the y hat, this is the predicted y. The predicted y is equal to a plus bx. Now, what do those other variables mean? Okay. Well, y or y hat, again, is the predicted value of the response variable y for any given value of the explanatory variable x. Explanatory x, kind of help remind us there. B is the slope. We've seen that before. It's the coefficient right in front of the x. That's the amount of which y is predicted to change on average when x increases by 1 unit. Remember that that slope is the average rate of change. Slope is an average. And then a is our y-intercept, the predicted value of y when x is equal to 0. So this is the form that we talk about it. Y, or the predicted y, is equal to a plus bx. So here we have an example of that relationship between miles driven and the price. We've already predicted and have the regression line from you. A little bit later, we'll talk about how to do it. So what we have here is we have the predicted price is equal to 38,257 minus 0.1629 times the miles driven, okay? So identify the slope and the y-intercept, the regression line, in interpreting context, always in context. So what do we have first? Well, I'm going to look for the slope that's there in front of miles driven. So we can see the slope is negative 0.1629. That makes sense to me that it's negative because I saw a negative slope or a negative association. So I want to look for that negative sign when I'm looking for the slope. And it's saying that that tells us the price of a used Ford F-150 is predicted to go down an average of $0.1629 for every additional mile. So we think about that as this being X or X over 1. So it goes down 1.629 for every 1 unit that the truck is driven. And this unit is miles. Okay. If we take a look at what we have here, this is the y-intercept. So here A is equal to 38,257. So what does that mean in context? Well, that means that the predicted price of the Ford F-150 that has been driven 0 miles. That's the predicted price of a brand new Ford F-150. Now, this may not be perfect, but what we do is we've grabbed these data points, we've found the line of best fit or the regression line, and this is what the model tells us, and that's how we would interpret those two in context. So then if we have a model, how do we make predictions from that? Okay, so we can use a regression line to predict the response y hat for a specific value of explanatory variable x. Let's use the regression line to predict the price of the Ford F-150 with 100,000 miles. So remember, this is a regression model that we had, and we'll learn how to do that by ourselves, but right now it's still given to us. So what do we have? We want to predict the price. We have the miles driven as 100,000, so we just pop in 100,000 into miles driven. Do the math, and we can see the price is $21,976. Remember, that hat, that over the price reminds us that this is predicted. We wouldn't say that that's what it is. We would continue to, from our model, say that's what it's predicted to be. So a Ford F-150 truck with 100,000 miles is predicted to cost $21,967. Tapping cans. So here's another model. Tapping cans, does this make a difference? And it would ask, don't you hate it when you open a can of soda and some of the contents spray all out of the can? Some AP Stat students investigated if tapping on the can of soda would reduce the amount of soda expelled after the can can have been shaken. For their experiment, they vigorously shook 40 cans of soda and randomly assigned each one to be tapped for 0 seconds, 4 seconds, 8 seconds, or 12 seconds. Then, after opening the can and cleaning up the mess, the students measured the amount of soda that was left in each can. So we're not going to do this here, but this is an experiment. You can think about kind of a fun way. What's the experimental units? What are the different random assignment here? What is the different treatments and that kind of stuff too. So some of a fun extra bonus here is to pause this and try and draw this experimental design. All right, so here's what we have. We have the data here, and we have it grouped because we had some that were tapped for only 0 seconds, some for 4, some for 8, some for 12. So we can see that they have some nice clusters there. Okay. So here's a least squared regression line that has been put from that. Again, we'll figure out how to do this ourselves, but this is what it's already for us now. So we're just looking at the interpretation. So if you interpret the slope and y-intercept the regression line, let's predict the amount of soda remaining for a can that has been tapped for 10 seconds. And let's predict the amount of soda remaining for a can that has been tapped 60 seconds. So interpret the slope and y-intercept the regression line. You're just looking at the 2.63, right? And we can think that as a slope, 2.63 or 2.63 over 1. So if we look 2.63, that's how much is left in the can. We can see that from slope is the change in y over change of x. So here's y, soda. Here is x, tapping time, so 2.63 over 1. So on average, we would predict that there is about 2.63 additional milliliters of soda left for every additional 1 second of tapping time. So 2.63 over 1. Predict the amount of soda remaining for a can that has been tapped for 10 seconds. All right, so I'm going to take this 2.48, 0.6 plus 2.63. And now my tapping time is 10 seconds. And I'm going to see that's about, I predict it's 274.9 milliliters. Now predict the amount of soda remaining for a can that has been tapped for 60 seconds. Well, that's interesting. That's off our graph. Let's take a look here. We're going to change this to 60. and that's about 406.4. So that means if you tapped it for more than a minute, there's a lot more soda in there. And maybe what we might find out, if you're a little tricky with your math here, there might have been more soda left in the can than what we started with. So I think that's a little bit dangerous here that we went all the way out to 60. And that kind of leans to this point here. Which prediction are you most confident in? The one for 10 seconds and the one for 60? I think what we're going to find is our 10 seconds that's here within our data set, our model is built around that, is something we can be a lot more confident with than what we can do with 60. Because if you think about it, tapping it for 2 minutes or 5 minutes or 10, there's no way we can produce more soda in that can than ever existed here. So that leads us to this idea, which is called extrapolation. When we use a regression line to predict the response y hat for a predicted or a specific value of the explanatory x, they keep saying y hat, but I'm going to switch more to the predicted y. The accuracy for the prediction depends on how much the data scatter about the line. So when we can substitute any value of x into the equation of the regression line, we must really exercise caution in making predictions outside the observed values of x. So let me go back here real quick. It's okay that we did 10 here because 10 was in our data set, but going for 60 is way outside our data set. So instead of interpolating, looking inside our data set, we're doing extrapolation, and that's a lot more dangerous. That's not something we want to do. So extrapolation is the use of the regression line for prediction far outside the interval values of explanatory variable x used to obtain the line. Such predictions are often not accurate. And I would even go as far as saying that don't make predictions using values of x that are much larger or much smaller than those that can actually appear in the data. And we'll just go as really far to say extrapolation equals danger. Let's say that right now. Extrapolation equals danger, okay? Don't be dangerous. I know some of you saying that extrapolation is your middle name, but not here, not in stats, okay? Use caution. So at this point, you can stop and kind of come back to this, but this is really at a place where we're ready to look at some ideas from homework 3. And I would also encourage you to look in your book or online book for extra examples if you want. So on this homework, remember, we're going to be focusing on interpreting the slope and y-intercept of the least squared regression line. Remember that slope is the average rate of change. It's the average rate of change, what we have in 1 unit in y over 1 unit in x. The slope is change in y over change of x. We also want to use the least squared regression line to predict y for a given x. So we're going to be having the equation. We're just going to be plugging values in. And we're going to talk about explaining the dangers of extrapolation. So if you feel like it, you can pause here. I'm going to move on in just a second, but pause here, kind of write down where you're at, try homework number 3, and come back. Okay. So let's continue on into section 3.2. So the next thing we want to talk about is residuals. Okay, the model isn't perfect. A lot of times, unless we have a data set that makes a straight line, we're going to have something that's going to be off. We're going to have some little bits of error here and there. In most cases, no line that passes exactly through all points in the scatter plot, okay, unless the line is perfect. A good regression line makes vertical distances of the points from the line as small as possible. We're going to see something of that. I'm going to try and show you some dynamic models of that too. So we have a definition here. We have a residual. A residual is the difference between an observed value of the response variable and the value predicted by the regression line. Okay. And we'll talk about this again when we have a picture in front of us. When we're finding a residual, we're always looking at the actual value minus the predicted value. And how do we remember that order? Well, a nice little thing that we have is actual minus predicted, AP, just like we have our AP stats here, right? Y minus Y hat, or Y minus predicted Y. Think AP, or actual predicted. So if we go back to that graph where we had the price in dollars and the miles driven, notice how our line cuts through all those points and hits almost no lines perfectly. That distance, that horizontal distance that we have from the actual to the predicted is called a residual. So here, if I look at this data point here, this was the actual down to the predicted. This distance here, remember in mathematics, we measure distance as a straight line. Okay? It is predicted here, and we can have residuals here above this actual minus predicted. So that's going to be a higher number minus a lower, so that's going to be a positive value. And down here, take a look at this. This data point was actually a lot lower than what was predicted. So if we did actual, a smaller value minus predicted, it would be negative. And I'll show you a little bit of that in just a minute here. So notice that we have positive residuals. Those are ones above the regression line. So actual minus predicted will have a big value here minus the predicted value, big minus small. That's going to give us a positive number. Negative residuals are below the regression line. We have an actual value that is small, and the predicted value is bigger, right? So we have a small number minus a bigger number, so it's negative. That would be a negative residual. So let's find and interpret our residuals here. Here is our least squared regression line again. The predicted amount of soda is equal to 2.48.2.63 tapping time. And remember that that is our slope, 2.63, change in y over change of x, 2.63 over 1. So on average, we would predict that for every 1 unit of x, for every 1 second, we predict it would go up on average 2.63 milliliters of soda. So let's calculate and interpret the residual for a can that was tapped for 12 seconds and had 290 milliliters of soda remaining. So we're looking at this point up here in green. Notice this has 290. That's a lot higher than what we predicted here with our regression line. So what happens, that becomes a positive residual. We have the actual minus the predicted. So the actual was 290, and the predicted takes our equation here and puts in 12 for the tapping time. The predicted y was 280. So our actual minus the predicted was about 9.84, and that distance is our residual, and that is above the line. That's a positive residual. Now, what about for number 2? When it said that it was tapped for 4 seconds and it was 250, that's down here. That's less than what was predicted. So what we see is it's going to be below the regression line, and it's going to have a negative residual. We take our predicted, again, here's our least regression line, and we put in 4 for 4 seconds, and our predicted was 259.12. Now our actual was 250. Our line was higher than that. It was higher than what we had. We predicted for it to be higher than what it was. So actual minus the predicted, the residual was negative 9.12 milliliters. So we can see we can have positive residuals that often fall above the regression line and negative residuals that fall below the regression line. So we have a least squared regression line. The different regression lines produce different residuals. The regression line, we want one that minimizes the sum of the squared residuals. Okay. So kind of the idea here of a regression line, we have what's called a least squared regression line. And we'll show you a picture over here, and then I'll show you kind of a more dynamic model that moves around. So what we do here is we take all of these points that we have here, and we draw the residuals. A quick vertical line from the actual point to what's predicted. And then what we do is we square those. This is a lot like standard deviation, where we have the median, and then we have points below the median and points above the median. And if we were to take those distances and add them together, we would have distances that were less than the median and above the median, they would cancel out. We can't have those cancel out. So in standard deviation, we square those before we combine them. So what we're doing is we are taking these, sorry for that pop-up, we're taking these residuals and we're squaring them and we're putting them together. And the smallest amount of squares that we have are the best. So let's pop over to a dynamic model here in Fathom. This is a model of carbs and fat, and we're going to see that with a relationship in a little bit about the relationship between carbs and fat in McDonald's sandwiches. So here I have all of these here, and I have some points that are above. Those would be positive residuals, and some that are below. This line coming through is my regression line. Okay. So what I'm going to do is I'm going to ask it to put the line of best fit or the least squared regression line for me. It's there. What I want to do is I want to make my residuals come in. So I'm going to have that here. So what happened is the residuals are in here, and we have the squares. Now, if we take a look, this one here, this is pretty much real close to being just as far above as this one is to being far below. But if we didn't take a distance and square those, these would cancel each other out. As the line moves from our different residuals here, these squares get bigger and smaller. Okay. If I take a point, so let's take this point right here. If I were to move this point, notice that the closer it goes to the line, that it has a smaller distance away. In fact, if it's on the line, it has no residual. Okay. If I were to take a point here and I move it further away, that's more of a square distance. Notice down here, what's moving is called the sum of squares. The residual model works really hard to minimize the sum of squares. Okay. So what happens is when that line cuts through, the line's cutting through and saying, okay, this is the smallest amount of residuals that I can have. And we notice that if lines are cut closer together, then they're going to have smaller residuals. If I try to take these points and get them closer to what we have here, right? If they're closer to making a straight line, then the residuals are going to be really small. Okay? But if I go back to original data and I see that those data points here are starting to get further and further away from what we had, or back to the original data, then we can have that line. So the line tries its very best to model that. And again, if we show our squares here, we can see that points that are far away have a lot larger residual. And again, we square those residuals, so we add them all up. It's a collection of what we have. This sum of squares right here, right? We're trying to minimize it. So we minimize the area that we have, and we have some great stats moves and pre-calc and calculus moves to minimize an area under a curve or to minimize area. So that's why the regression line is very often called the least squared regression line, because we're looking for the smallest value to square our residuals. So here's something we're going to practice. We're going to do this. We're going to say, fat and carbs. The data below is for 9 McDonald's beef sandwiches. And you can find this example in packet page number 8. So we have a data set of these 9 sandwiches, and we have a relationship between their carbs and their fat. Okay, and that was back here. That's what I have in my original data set here. So we can kind of see what that scatter plot looks like. And then we're going to work there to see what we can get. Okay, so that's going to be our scatter plot here. And we're going to work on putting this with our calculator. So once we do that, we're going to enter the data into the list. We're going to use the calculator to get our least squared regression line. We're going to write out the least squared regression in context. Remember that it's not about y's and x's. We're going to look towards kind of old school, do with the correlation coefficient, and what 2 things can we tell you about the relationship. Some rehashing of 3.1. We're going to interpret the slope in y-intercepting context. So that's what's new about 3.2. And we're going to calculate and interpret the residual for the Big Mac. So the first thing I'm going to do is I'm going to help you get this going in our calculator, and then we'll switch over to our answers and see how you did. So make sure that you're practicing this yourself and trying to get your ideas on your packet first, and maybe pausing. I'll remind you just a minute where to pause before you go and look at the answers. Try it before the answers, okay? Allow yourself to make your mistakes instead of just looking at the answers and copying from there. So I'm going to go to Stat, and I'm going to go to Edit, and I've already put my points in. remember that we're just putting our x's in. This is going to be our carbs, and our y is going to be our fat. So when we get the slope, the change in y over change of x is going to be the average change of grams of fat over our average, over our change in carbs. So what I want to do here is there's a couple things I can do to get to this data. Again, remember I went to stat. So if I wanted to plot it, I would go to second stat plot. And I'm going to turn that plot on. And I can see that this is going to be a scatter plot. And I have list 1 and list 2. So I'm going to zoom. I'm going to zoom to my stats. I'm going to take a look at that plot right here. So here's what we have. Remember that we can hit trace and look at different things here. So as I go right, I can look here and see, okay, this is the plot. This is the 40, 26. So this is the sandwich with 40 carbs and 26 grams of fat. So that's something we can do that's really nice, is we can make that scatter plot. Okay, so we can copy that. We'd want to make sure that we're labeling our axes, both X and Y. So there's a nice way we can do it. If you're drawing out your scatter plot, that's okay too. So the next thing we're going to do is we want to make a least squared regression line. So we're going back into stat, but now we're going to go to calculate. Remember that the form that we're talking about in our book is down here in 8. This is the line of regression, or regression line, a plus b of x. So I'm going to hit enter there. It's going to ask me, where did I put in my x? Or where did I put my x values? I put those into list 1. And if this is cleared out, you can't remember, that's just above the 1 right here in blue. So I'm going to go second 1. That's going to be my list 1. Now I'm going to go to list 2. Frequency should be cleared out. Store regression equation to be cleared out for now. And I'm going to hit calculate. So notice here in my calculate, I get a lot of great things. And we kind of saw this before too. This was kind of the way that we snuck to see what r and r squared was. So here is my equation. Y is equal to a plus bx. A is the negative 40.2 and b is the 1.71. So my predicted y, it would be my predicted y, or my predicted fat, is equal to negative 40.2 plus 1.71 x, or what we would have for the fat here. So let's go take a look at the work on the next page. Pause if you haven't yet. Try some of these yourself, thinking about how you would do this in context. And now we're going to take a look. Quick pause in case you have to run back to your screen here to do it. All right, we're going to the next one now. Remember real quick, if you're not seeing the r and the r squared, that we should go through these steps to turn it. We talked about it in 3.1. You don't have to do this often unless your calculator is reset. But just a quick reminder that if you don't see the r and the r squared, you have to turn your diagnostics on. And this is the screenshot from 3.1, how to do that. All right, so here's our key. We can see that carbs was our explanatory value and fat was a response variable. So we write it out in the least squared regression line. Y hat, or predicted y, is 40.2, 1.71x. Let's put that in context. So remember that y is fat, so that's our predicted fat, is equal to 40.2 plus 1.71 grams of carbs, okay? Now from 3.1, what does r mean? We can see r is 0.743. What's the correlation coefficient? What are two things that we know? Well, we know that we can see that it's like a positive correlation, and so we can see it's a positive direction. That means as carbs increase, the fat tends to also increase. And we can also see from the r being close to 1 that it's a strong linear correlation. So that's really nice. So let's interpret the slope and y-intercept here. I kind of put y over x, so I have 1.71 over 1. So that's 1.71 grams of fat over 1 gram of carb. So remember that this is a prediction and it's on average. So when you interpret slope, you need to do that. You need to put on average, because that's what slope means. And to tell them that we're working on this model, we need to have a prediction there. So what I have is for each additional 1 gram of carb, the fat amount is predicted to go up to increase on average of 1.71 grams. So important here to have the predicted and the on average. The predicted is telling us that we're using a model. The on average tells us that we know what slope means. What about the y-intercept? When the carbs are 0 grams, the amount of fat is predicted to be negative 40.2 grams. Now we know that's impossible, and we might have to interpret sometimes in context that when you have 0 carbs, there's actually a negative amount of fat. Sometimes I'll ask you to interpret that in context, but that's what we have here. That's what the model tells us. Calculate and interpret the residual for a Big Mac. That's the one that has 45 grams of carbs and 29 grams of fat. So mark it on the scatter plot. So if we look on the scatter plot here, we can see that we have an actual, it's 29, but it was predicted by our model, and we put the prediction right in here, to have 36.75 grams of fat. So we do a residual, actual minus predicted, AP. The actual was 29, and the predicted was 36.75. So that's about negative 7.75 grams. So what we say is that Big Mac actually has 7.75 grams of fat less than what we would predict by our model. Okay? So that's a really nice sum up of kind of using our skills from 3.1 and 3.2 back here on our page, packet number 8. So this would be a great time to take a break and do homework number 4. Just kind of doing baby steps here. Now, it looks like we're not doing too much between it, but it's really the precision that we need in these interpretations. That's really where the points lie. That's really what we're looking at. So remember, we want to calculate and interpret the residuals in context. We want to explain the concept of least squares. We use technology to find the least squared regression line, and we found slope and intercept of least squared regression line from the means and standard deviations of x and y and their correlation. That last one, we don't have as much, kind of finding it by hand. That's something that is almost never on the test, and we're super predicting that it's not going to be here on ours either way. We'll look at it a little bit and kind of talk to you about how that works, but it's not something that we have to worry about at this time. So we're going to take a pause in just a second, and then we're going to move on to the next section. If you're stopping here, that's great. Just pause your video, kind of write down somewhere to you where that minute was, so you can come back and look at it. I'm on a roll, so I'm going to keep going. All right, so let's take a look at what's next, what's called a residual plot. One of the first principles of data analysis is to look at an overall pattern or striking departures from a pattern. Remember that when we're looking at data itself, we're looking for patterns. We need that to try to do the interpretation. A regression line describes the overall pattern of a linear relationship between two variables. Very important. Remember, our line of best fit, a regression line, is to look at the linear pattern here. So we can see departures of that by looking at residuals. So what we can do is we can do what's called a residual plot. And a residual plot is a scatter plot of residuals against the explanatory variable. So residual plots help us assess how well a regression line fits the data. So we basically plot the x variable in the x's and the residuals in the y to try and see what we have. Let's take a picture of this. So here's what we have, back to the truck example. This is what we have as miles driven, right? So this is normally what we have. This is the x, miles driven, and the y, price in dollars. But what we can do here is, here we have an actual residual plot. So what this has done is we still have our explanatory miles driven, but what we've done is we've done the residuals here. Now I want to show you something really cool. I'm going to pop out of my presentation real quick. And then we can talk about a residual plot here for the McDonald's fat data. Okay. So really what I want to show you here is that this line of best fit and the residual plot, they have a really nice relationship. See this line of best fit here that's coming down, that's decreasing? In a residual plot, this line of best fit kind of becomes our horizontal axis. So if we take a look at this, and I'm just going to rotate this a little bit. So, and look at this line here, the patterns that we see here in our actual scatter plot are kind of more to scale in the residual. So that's what it really does for us. It lets us take, with a residual plot, our line of best fit as our horizontal axis, and let us take a look and see that pattern. I can kind of see a little bit of a sinusoidal. Maybe it's a little bit of a curve here. And I'm probably just trying to look for that so I can say the cool word sinusoidal. But see, I still see that kind of bend here and here. So a lot of times when we're looking for a residual plot, we can think about it as it just being the line of best fit, and here what we have. And that's a nice quick way on a test too, to try to line up a line of best fit with its residual plot, is to kind of do that little shift. And let us take a look there. All right, let's gonna jump back in and do a residual plot for the McDonald's data here. All right, so what's really nice about when we have this data is that when I ran this line of best fit, it may not look like it because something happened in the background, but all the residuals were actually created for us. That was pretty neat. So if I go back to my stat and I go to edit the different lists that I have here, I can see all my lists here, right? But if I go into stat and I go second lists, what I can see down here is I have what's called a resid. So I can see that I can put my residuals, whoops, sorry. I can go here and I can see that residual list. Now I can, if I want to, just go to second list residuals and go here and see that kind of listed out. These are all my residuals that I have, and that's kind of hard to read them, right? Those are all the residuals. So every time I make a line of best fit, the residuals are calculated. So what I like to do is I like to go into stat, edit, and I like to put my residuals next to my data points. So I'm going to go over here. Here's my X, here's my Y. I'm going to go up and I'm highlighting right now, highlighting list 3. Now I'm going to go to second list and I'm going to put the residuals in there. And what that does is that automatically lines up all the residuals. Remember when we were back, I'm going to go back here to our McDonald's here. We had to find the residuals for the Big Mac that was at 45.29. Take a look, 45.29. And then what we have here with a little bit of our rounding error is the 0.787. There's a nice residual there. It's a little bit more precise what we have. So we have the data points and the residuals here. That's really nice that our calculator can help us do that residuals. So what does residual plot look like? Well, remember that our residual plot is going to have the X value here and the residuals. So I'm going to go back. I put my residuals here in list 3 to my stat plot. I'm going to go to stat plot on, and I'm going to have my residuals here I have stored into list 3. So I can go to second list and I can pick list 3, or if I forget where they go or I didn't put them in list 3, I can just say residual here. So residual plot is X versus the residuals. Zoom to my stat plot, and here's my residual plot. I can now trace, so I can go through and look at my X values and see what the associated residual will be. Again, that's nice. Here's my 45, my Big Mac, and I can see the residual would be negative 7.87. So in a residual plot, we can look here and get those values. What we're really looking for here is we're looking for any pattern that we can see. If it's a curve, we know that maybe there's a curve in the original data, and a residual plot tells us that the line, a linear model, is not appropriate here. So that's how we look for a residual plot to try and figure that out. So let's take a look here at another example. Here's an original data plot where we see an obvious curve. And we can see that in the original plot, it makes it more profound. So you may not see that curve may be so small that you can't see it in the original data, but a residual plot really makes that pop. If you can see any of our, any curvature here in the residual plot, then that warns us we might have some danger here and we may not have an appropriate linear relationship that we can model. So way back when, I can't remember if we have done this yet, but this is our monopoly scatter plot. So this is a scatter plot of how many points you are around, or I'm sorry, how many spots you are around a monopoly board. And then what you have is what the value is. So we have some outliers here. It doesn't matter where you are in the board, the railroads 1, 2, 3, 4 are always the same price. So we see that here. And then we also have the utilities here. So we would take a look and say, is your linear model appropriate here? Well, we kind of see a weird pattern here. It's not a nice one here. It kind of goes up and down. We're not seeing that straight model here, so it might be something that we're worried about. Again, if we took a look at our model here and here, we can see that simply our model kind of rotated to make that flat is what we see for the residual plot. Okay. So that's taking a look at it here. Notice that when we do our models, when we do our stat calculate line of best fit, we've been talking about R and we've been talking about R squared. And before, when we have R and R squared, we were using R to talk about the correlation coefficient. Well, R squared has a really cool name. It's called the coefficient of determination. If you're looking for a cooler variable than that, you just need to stop. There really isn't one. The coefficient of determination. The coefficient of determination is the fraction of the variation in the values of y that can be accounted for by the least squares regression line, the relationship between that y and x. And we're going to interpret that a little bit more in context to tell you that. But that is really cool. Okay, R squared, the coefficient of determination. R squared basically tells us how much better the least squares regression line does at predicting the values of y than simply guessing the mean y for each value of the data set. So let's go back to the price in dollars and the miles driven. For this data set, R squared was 0.72 or 72%. Okay, so what does that mean? What that means is, well, first of all, I guess, if it's 0.72, then what is R? And that's pretty easy, right? Because if we know R at 0.72, that's R squared, right? Then we'll just take the square root of that. Oops, got my imaginary number in there. 0.72. There we go. All right, so there's my R, about 0.84. Okay, so that's pretty easy, just taking the square root. And then so we want to interpret R squared. That's new to us. What does R squared mean? So here's how it looks. Here's what it looks like. 72. 72% of the variation in price is explained by the linear model relating miles driven and the price of the truck. That's pretty cool, okay? So we're saying that 72% of the variation in price is explained by the linear model relating to miles driven. So, okay, well, you're like, well, 100% minus 72, how do we explain the other 28%? And that can be a variety of things. That could be the options that are on the truck. That could be the brand of the truck. In this case, this is Ford F-150, so that's not something we do here. So a lot of times it can be in the region that you're buying it from. But a lot of times I'm going to guess that it's going to be the options that you put on a truck, right? The size of the engine, or if you have safety features, or if you like those big rims, right? If you have the moonroof, if you have the tow package. So this is a pretty good model. And we know that from our R being 0.84, that's pretty close to 1. That's pretty strong. It's a strong relationship here, but R squared is really nice. It really tells us the percent of the variation in price that we can attribute to this linear model with miles driven. So that's really neat. And of course, obviously, we're going to see that if we have a stronger R squared, we're going to have a stronger R. And doesn't that make a lot of sense that if we have a very, very, very strong correlation, then our model is going to do a really good job explaining that association between Y and X. So we really don't have to worry about how to do those by hand, the R squared. Another thing we don't have to worry about by doing by hand is called S, and that's the standard deviation of the residuals, okay? So S is going to be given to us in almost every case now. So if we want to assess how well the line fits the data, we need to consider the residuals for the observation, not just one. We take a whole collection of the residuals. And then using the residuals, we can estimate the typical prediction error. Now, where did we hear typical before? We heard that in standard deviation. Standard deviation with a typical amount that an entry can vary from the mean, right? So if we take a look at that and we want to see the typical amount that it can vary. So if we take a look at S, it's the standard deviation of the residuals. So what's the typical amount that we have for residual? And remember, a residual is an error in the prediction and the actual. So this is really the typical error. So the standard deviation of the residuals, or S, is the typical prediction error. So let's go way back in section 3.1. We were talking about points per game and the number of wins down the SEC, right? And so we have this scatter plot. So we bring it back. Here's the equation, the least squared regression lines for that scatter plot. Also, let's see, we see that S is equal to 1.24 and that R squared is 0.88. So we're going to talk about going back to what does this all mean? So kind of practicing here, again, this data set, what does all this new stuff mean? And also we can see the nice residual plot next there to the line as well. Okay. So first of all, let's calculate and interpret the residual for South Carolina. They scored 30.1 points per game and had 11 wins. Okay. So the predicted amount for South Carolina is, well, remember that y hat, or the predicted y, from our line of best fit on the previous slide, was negative 3.75 plus 0.437 times the points, or we're going to put the points in of 30.1. So that is a predicted wins of 3.4 wins. Now, the residual is actual minus predicted. So what we had was, we had an actual wins was 11 minus predicted wins of 9.4. So that was a predicted 1.60 wins. So South Carolina won 1.6 more games than was predicted based on the number of points they scored per game. Let's consider the linear model. Is it appropriate for this data? So we take a look at this data here. I don't see any obvious patterns. I'm looking for curvatures. I'm looking for bends. It kind of looks like it just spread out or as a cloud. So I'm not too worried about it. So basically I would say because there's no obvious pattern in the residual plot, the linear model is appropriate. Let's interpret the value S is equal to 1.24. Do you remember what S is? All right, I'm going to give you a pause. Think about this yourself. Pause the video and answer this before I show you the answer. All right, don't just wait. Hopefully you've tried this yourself. Think about what it is. Okay, here we go. When we're using the least squared regression line with X points per game to predict Y number of wins, we're typically going to be off by about 1.24 wins. So again, S is the standard deviation of the error rate of the residuals. So typically that's going to be how far our model is. Remember that the word typically is used in standard deviation, okay? It's not the average. We can't use that. It's not the average. Average goes with our slope. We have to be very careful. We're using average with our slope here. Typical, or the typical amount, is with our S's here. And then R squared, the coefficient of determination, is 0.88. What did that mean? All right, answer it for yourself. I'm going to give you the answer. I'm going to click it soon. Try to think about what it is first. All right, here it goes. Hope you've thought about it already. About 88% of the variation in wins is accounted for the linear model relating wins to points per game. Okay? So that's good practice trying to run between those two there. So this is a good time to take a break and stop and work on homework number 5. In homework number 5, we're really working to construct and interpret residual plots to assess if linear model is appropriate. Thinking really a lot about doing that on our calculators. Using the standard deviation of the residuals to assess how well the line fits the data. And then using R squared to assess how well the line fits the data. And then interpret the standard deviation of the residuals, that's S, and R squared in context. So if you're stopping to do your homework here, kind of look at the video, see where we stopped, and then come back and join us. I'm on a roll. I'm going to keep going here. All right, so we told you before, or I told you before, that a lot of times this is going to be given to us. So kind of the standard way, or a way that they give us the data, we won't necessarily see screenshots like we do here in our calculator when we're doing the line of best fit. A very common way that we do it is a statistical package called Minitab. So in Minitab, we want to make sure that we can see all of our points here. Notice that we have our miles driven, so that is related to our X. And again, we're back to our truck and our slope, right? Our truck, the miles driven and price. So here we have the miles driven, so there's our slope. There's where our y-intercept is. And then S, we know that's a standard use of visuals, so S is nice. S is S, even though we have a capital here. And then R squared is going to be right here as a percentage. So we want to make sure that we can grab that data out of a Minitab. That's very common to how they would give us the data in a graph, in kind of a data display here, which is Minitab. And a lot of times you're just going to tell us that R squared equals this, S equals that. Here's the slope, here's the constant. Remember that we did this in chapter, we're doing this in chapter 3. We're doing this till the tail end of it. But actually, this is something that if you are working from chapters 1 to 12 or 13, someone did really early in the semester, right? So this is something that was definitely covered by all groups. So just because we are doing this here at the end doesn't mean like, oh, they probably won't have it. We're really want to know and talk about what this is because it's important here. We think that it's going to pop up. Okay. So here's an example, just a quick one, that's from the 2012 AP Stats multiple choice. And this is in your packet on page 10. So the question read this year, the computer output below shows the result of a linear regression and analysis for predicting the concentration of zinc in parts per million from the concentration of lead in parts per million found in fish from a certain river. So notice what we have here is we have the Minitab output. And it's really important as for now. Here, S is really easy to find. R squared is easy to find. We have the slope here, and we have our constant here, which is 16.3, okay? So let's take a quick pause and just try to figure out what is the correct choice here. Which of the following statements is correct interpretation of the value of 19? All right, let's sneak back. What was 19? All right, 19. Okay, that looks like it's going to be our slope. So remember that slope is change in y over change in x, predicting zinc per x. So we're looking at our zinc is going to be our y because that's what is predicted, right? So we take a look and average, there is a predicted increase of 19 parts per million for every zinc for every 1 concentration of lead. All right, so that's what we're looking for here. We're looking for B to be an answer. A is not our answer because it switched the X and Y. C and D are both trying to pretend that 19 was our y-intercept. And notice E, they're sneaking in and trying to get here. This is how we talk about what S is, but we know that S isn't 19. We can say that S is the 16.17 here. Okay. So if we were doing this by hand, which we don't have to worry about, these are equations that we would use. This is very not often used in a normal year, and we don't think that we would have it. But this is what would be nice. This is how we would find what the slope and the y-intercept would be. So slope is very easily just taking our r and multiply the quotient of the standard deviation of y or the standard deviation of x. And the y-intercept is by taking what we have for our mean of y minus b times the mean of x. So we can see that we could create this line of best fit ourselves just by taking x and y and finding the means and the standard deviations. So it's not something that we're going to focus on, but it's something to know. One little thing that's really nice to know here, and sometimes it pops up, but more in the multiple choice you have to worry about, is the line of best fit always goes through the point mean of x, mean of y. It always cuts to the middle, kind of like a teetering point there. So this is what your formula page looks like. We can see that it will remind us that y predicted is a plus bx. And if we needed to find those b's and the y's, they're there. Again, very uncommon that we have to do that in a normal year versus this year, but it is on our data. It is on our equation sheet. Another thing we want to be careful of is talking about outliers and what's called influential observations in regression. So an observation is called influential for statistical calculation if removing it would markedly change the result of our calculation. Points that are outliers in the x direction of a scatter plot are often more influential for the least squared regression line. So if you were asking me to mark a point on the scatter plot that would have a large residual but not be very influential, a large residual would mean that it's really far away, but non-influential means that it's not far away in the x direction. So here I have a point here in the y direction. This has a very large residual, but it's not far away from the data in the x direction, it's in the y direction. So this is going to be a large residual, but it's not very influential. What if you were asking me to mark a point on a scatter plot that would cause the slope to increase significantly? So where I might mark this point is up here. Notice that this is far away from the x. This data is probably centered about right here. So when I put an x away from that center and far away, the line of best fit is going to chase that line. And I'm going to show you a dynamic model in just a second. But if I did this here, this line is going to chase that line. It's going to change and it's going to make the slope go up. What if you asked me on a scatter plot to make a slope that would decrease significantly? Well, then I'm going to put the point down here because this line was going up, it's positive. But if I put that point down there and this line is going to chase that, it's going to teeter-totter. Let me show you something real quick. Let me pop out and show you this in Fathom. So here I have this again. I have my carbs versus fat, and I'm going to put my regression line in. Where'd it go? There it is. Okay. So if I take this point right here, notice that when I take this point, I'm going to make this a little bit bigger. We can see down here, here's my R squared. So only about 55% of the variation in fat can be explained by the linear relationship it has with carbs. I'm going to take this point and I'm going to move it. Notice that when I move it, the line changes a little bit, but my R squared doesn't change that much. And that's because I'm kind of sitting here in the middle of the data, right? So I can still have a big residuals. Now it is changing the line a little bit, but not too much. Now, look at the big difference here when I'm moving X. Notice how the line chases it. I'm moving it down, so line is moving down, right? If I pop it and go above, it's chasing that. This is super influential point. This one point being far from the data is just making that line change. It's making it chase all over the place. Again, points within the data, not too much here. Now, allow me, if I may, to move out a little bit here. So I'm kind of zooming out a little bit, right? Notice again that a point that's close to the data here isn't changing too much. But this point here, let me move it now even further away in the x direction. All of those points on the left show a positive relationship. But this one point, because it's so far extreme out here, right? That one point is so influential. Look how it's dragging the line towards it. No matter where I go, that line wants to chase it. That's just terrible. This is an influential point. If I were to move this influential point, let's say I were to remove this point here, I'm just going to delete it. Well, I just deleted the whole graph. That's not what I wanted to do at all. Let's try that again. Let's say I just take this point here. I'm going to get rid of that point. I'm going to cut that case. Notice how that popped, okay? By putting that point in and then removing it, that drastically changed what we have. That point is influential, okay? I'm going to put that point back. I'm going to put that point kind of back where it was before, kind of over in here. Now, what would happen if I were to delete this one right here, 8? Let's delete that case. Wow, that didn't really move at all, did it? See that again. Here's this point. I'm going to make it go away. Because removing that point didn't really change that, that point is not seen as influential. So again, an influential point, right, is a point that would markedly change the result of the calculation if I were to remove it. So let's talk about things that we've learned about regression and correlation, some things we have to be careful of, and some things we have to watch out for. Number 1, remember that correlation is the distinction between an explanatory and response variable. That's important in regression, okay? We need to know which one's explanatory and which one's response, because X is trying to explain what Y is doing. X is trying to explain the response that Y shows. Okay. Here, miles driven and price in dollars, if I'm saying that the change in miles driven expands the price, take a look at what happens if I change that. If I do price in dollars per miles driven, okay, that's a little bit different. But would it make sense to say that I'm going to use the price to predict the miles that are driven there? Okay, maybe it does. Maybe I can say that a higher price, which we see here, right, means that there's less miles driven. So we definitely want to make sure that we take a look. By switching the x's and y's, notice that the r squared didn't change. The model is still as effective or not as effective as we saw, but we really have to be careful because both our slopes and our intercepts changed. So it's really important that we're distinguishing and talking about the explanatory and responsive variable. Another thing that's important is that correlation and regression lines describe only linear relationships. This is one of those things where you really have to be careful and you have to catch this by yourself. Remember that when we're doing hypothesis tests and confidence intervals, the calculator doesn't know to check the conditions for us. It just does it. We have to check it for ourselves. Notice that in this first example, maybe it's appropriate here to use the model, but this definitely isn't looking at the curve. This one, a model here, we would be worried about that one outlier. And this one here, we have a whole grouping and then we have a point out. But guess what would happen if we were to actually run the model on every one of these? Every one of these would have the same correlation coefficient, where only it was probably perhaps appropriate to use a linear model here, that linear correlation coefficient. So we have to be careful. We have to know when it's appropriate to move forward, because if we ask the calculator just to do it, it can't catch that for us. Another thing that we have to be careful of is that correlation and least square regression lines are not resistant to outliers. We saw that when we were looking at influential points, that your line is going to chase those outliers. And the further away that they are in the x direction, one point can really mess that up. So we have to be careful. Our lines are not, our regression lines are not resistant to that. So we have to be careful when we see those outliers and trying to guess what the model is there. Okay. We can see kind of a bounce around here of just by popping in and out this 19th child. So basically we have this set of data, right? And we pop these points in, and just by popping in points that are here far away from the X or here far away in the Y, that we can change those models. And again, notice that this child 19 was popped in. It didn't really change too much because it was a movement in Y, but child 18 here has popped out. It really has a line chasing that from what we have here. Another thing that we really need to be careful of is association or correlation does not imply causation. Remember that there's no causation without experimentation. Another big thing we have to be careful of that they're always going to try and get you on is correlation does not mean causation. When we study the relationships between two variables, we often hope to show that changes in the explanatory variable causes changes in the response variable, and a strong association between the two is not enough to draw those cause and effect. If we want cause and effect, we're going to have to do that experiment. So sometimes an observed association really doesn't affect that cause and effect. An association between explanatory value X and response variable Y, even if it's very strong, is not itself good evidence that changes X and actually changes it. Remember, we've talked about probably in class how we would have when we have a fire, right? We would say that when there's more firemen or when they show up, there's more property damage. And maybe we were looking at that data and we're saying, wow, the more fire that we had, the more firemen that show up, the more property damage. Does that mean that even if there is a strong correlation, that more firemen showing up is causing there to be more property damage? There's probably a confounding variable there. And the confounding variable there is probably the strength of the fire. The strength of the fire, if it's a stronger fire, it's going to have not only more firemen showing up to try and fight it, but it's going to have more property damage. So we have to be careful just because we see that association, it can't be that causation. I love this comic. I used to think correlation implied causation. Then I took a statistics class, now I don't. Sounds like that class helped. Well, maybe. Classic. Please remember, correlation does not mean causation. In this section, we did a lot of things. We talked about how to interpret the slope and y-intercept of a least squared regression line. We use the least squared regression line to predict y for the given x. We calculate and interpret the residuals and their standard deviation. We explain the concept of least squares. We determine the equation of the least squared regression line using a variety of methods. Construction and interpret residual plots to assess whether a linear model is appropriate. Assessed how well the least squared regression line models relationship between two variables, and described how slope, y-intercept, standard deviation of residuals, which we call S, and R squared are influenced by outliers. So what is it time to do? It's time to do homework number 6 and then move on to the chapter review. Remember, in homework number 6, what we're focusing on is identifying the equation of the least squared regression line from computer output. We want to make sure we talk about why association doesn't mean causation, and then recognize how the slope, the y-intercept, the standard deviation of the residuals, which we call S, and R squared, the coefficient of determination, are influenced by extreme outliers. Okay. So again, just take a look, see what we have here. Go back to those dynamic models if you want to take a look. Reach out to us if you need some more help. And we should be looking at homework number 6 and the chapter review. Thanks for joining us. I hope that that helped out a little bit. And I hope that if you have any questions that you're reaching out and getting some help. Okay. So I'm going to stop the recording here and I look forward to your questions.